Good morning, everybody. I like the presentations we've had so far. They've been really interesting. So first I want to start off with a quick update on QUUB. For those who have followed us over the last couple of years, you've seen us do a couple of weird things. The biggest update is my team. Okay? The first time I came out here, there was me and my wife wasn't part of the team. And now this is just a few of the folks who are working with us at QUUB. I want to identify 3 of them who decided that they would brave the trip over and come with me and have to live with me for 4 days. We have Phil, 𝗖cie, and Nick. Phil's he handles all of our data. 𝗖cie, she makes everything happen. And Nick is our lead engineer. They're all geniuses in their field, so I appreciate that. But these are the number of people we have working, with the exception of we've added 3 more since I made this slide. So we are growing. All right, come on. So some major achievements. We have a project we want to talk about later that's coming in 2024. But we've actually gone and created a subsidiary here in the United Kingdom. We're working on a water project. And you can just see we've got a lot of stuff that we've done. That 5th consecutive SBIR from the United States Air Force has been amazing. And it's part of what we're going to talk about here today. Okay, so why lasers? Let's just speed. Okay, let's face it, a laser can be 1,000 times faster than an RF signal when properly attuned. And as long as you've got the ground stations, this will work just fine. Security. Okay, anybody can eavesdrop on an RF signal. It's a little harder to get a laser. Okay, so when you're at 350 kilometers up and you start with a 30 millimeter aperture, you're going to have a beam that's about the size of this room when it hits the ground. Okay? Unless you're in this room, you are not getting that signal. You can now see why the United States Air Force is interested in this. Okay? What I really love, though, is reduced regulation. There is no ITU is involved in this. The FCC is not involved in this. There are no regulations with lasers yet. And so as long as that holds, this is a great opportunity. Okay, so we had to put some hardware together and see if we can get this to fit into a PocketQube. Now, we do have a 6P PocketQube. I know it's an expansion of the standard, but it still follows the standard. But this is what we needed. Hello? Okay, there we go. This is what we needed to do to make it work. So in our tests on the ground, we used 650 nanometer lasers, but for space operations, we're using 1550 nanometers. Does anybody have an idea why we might choose that particular wavelength? Exactly. The atmosphere is invisible to this beam. It goes straight through, which is wonderful. If you try 650 nanometers through Earth's atmosphere, it's not getting very far. So we've got that laser. We had to introduce mirrors into this. These are micro actuator mirrors. They're piezoelectric units. And oh my goodness, are they expensive. And then our ground station is a simple Schmidt-Cassegrain. You can buy this off the shelf. They're about $5,000 US. It's a regular telescope, but we use this photoreceptor that's filtered to 1550 nanometers for reception. Okay? Now, we thought we were doing pretty good. This is some neat invention, only to find out that MIT had done it a few months before us. They actually launched a CubeSat that does everything that we're doing here. Same frequencies, same everything. I'm like, oh, great. All right. Now, here, I really want to highlight this little gadget here. This is our controller. We call it a QUUBICO. It is a custom-built Raspberry Pi RP2040. This is an amazing little gadget. You'll see that on this particular version, this is just our connector set. This can be turned into any sensor. So the QUUBICO is manufactured using high temperature methodology, and then we attach the sensors using low temperature solder, and it can become anything that we want it to be. It's a really neat concept. Okay. So we put together some ground tests. That's Nick there. This is one of our short range tests. We got up to 100 meters with a 0.5 milliwatt laser in 650 nanometers. Okay, so you do some math and extrapolate it out, and it says, okay, well, how much power do we need in space to guarantee a signal? And it turns out to be only 400 milliwatts. Okay. Before we had those tests, we bought a 7-watt laser. Do not use one of those. I'm just going to warn you that right now. Do not use a 7-milliwatt laser. It's a quick way to blind yourself. Nick is actually laser safety certified, and that was a fun course, but he did all of the work to keep us safe. So he developed this. We used the entire Pico drivers. It was a pulse driver. Okay? You cannot run these lasers in continuous mode. You can't get rid of the heat. Total transmission time is 90 seconds before you start to overload. All right, you just got, there's nowhere to go with heat. That's the biggest problem, okay? And then our flight expectations, we were able to test, again, extrapolating out communication to 1,000 kilometers, so we'll have complete view of the sky as the satellite's going over. And 1 megabit per second communications is what we're expecting as the bottom. And we believe we can hold that as a stable connection, okay? So we did a lot of tests, and, well, it works great. But here's the thing. Is it actually possible? Well, yeah, power is your biggest issue. Well, one of the biggest issues. There are a lot of issues. Let's just be honest, it's a laser. There are a lot of issues, okay? Power is a big issue. You've got that 400 milliwatts of laser, but that means you have to have 10 watts of system power in order to maintain it, and that doesn't include shedding heat. Okay, so how do you get 10 watts of power into a PocketQube? Well, I think, Alba, you guys have the most powerful PocketQube on the planet right now, so you might be able to do this. Heat is definitely the primary issue because, again, you have to pulse the laser. 90-second transmission time. That's it. You're done. If you push that beyond that limit, you are dead. Your satellite will actually start to melt down. Not a good look. Okay? And there's a large cool down period. So if you fire the laser, even at these particular altitudes and with temperature, you get 1 pass. Then you're going to have to wait at least 48 hours before you try it again, just to get rid of the heat. Unless somebody has a better way of getting rid of heat in a PocketQube, it's just not going to happen. Okay? How do you find the satellite? Whoops. How do you find it? How do you find the satellite? You're using a laser. Okay. Are you going to rely on just space track to get you the information? Well, you can put in an RF beacon. Oh, we're back to the ITU again. So there's almost no way to escape it. But there's also another option, that's an optical beacon. Now, you'll notice that when you look at the Aurora, and I think I'm going to try and back this up. I have no idea if this will work. Okay. So you look at the Aurora here. Those are actually LED cobs that we're going to pulse. So when we know when the orbit is about to start and we're going to do our view, we're going to use the telescope to lock in on an LED visible light pulse. That's how we're going to find it and avoid the ITU. Okay. But we have a redundancy. The way we build our satellites is to have, we expect failure. Okay. If you build a satellite and you expect it to fail, you can build it robustly. So know that it's going to fail, but understand how those failures could possibly happen and then build your satellite to compensate for it. So we also have an iridium on board. So absolute worst case scenario, we can at least get GPS coordinates of the satellite and extrapolate from there. This also helps with space track, because if you deliver your GPS location at a specific time, they can find you faster. Okay. So that's what we've done. We've actually put an iridium inside there. So all else fails, and yeah, we will have all 3 of these. So we're going to do the RF beacon. Yes, we started the licensing. The optical beacon and the iridium connection, just to verify that this laser is going to work. Okay. And we're going to be testing it in orbit in 2024. This will actually launch in October. So it's been a long, hard road. And I don't get into too much of the technical detail because that's what the Q&A is for. Okay? Here's the outline. We'll go from there. Okay? So when you're looking at doing this laser stuff, is it possible? Yes, we believe it to be so. We're going to prove it. That's the difference. It's like, well, it's a wonderful thing to have a theory, but now we're going to turn it into practice. If this works, this could be a game changer for PocketQube communication. Right? Imagine being able to send large amounts of data without having to deal with the ITU at any given moment. Right? That makes constellations incredibly capable now. And that's where we see the advantage. Okay? Short, simple, to the point. Do you have any questions, comments, or disparaging remarks? We take it all.
Thank you for the presentation. Since you're talking about the lasers, you need to point this laser. You didn't have anything about the ADCS. Can you talk about it? Did you build it yourself? Are you buying it? Or do you even have an ADCS?
Yes. Okay, so this is where that whole redundancy thing comes in. Yes, we have an ADCS. We have a 3-axis reaction control system, and we have magnetorquers built in as well. But if both of those fail, we have a gravity gradient. The spacecraft is actually designed to point down. That means that our communication time is a mere seconds, but because we can't aim it, it'll only be pointing straight down. And so we've got that window. So that's how we're planning on doing that. But we have our own, we built it ourselves.
Okay, and then just one more quick question. What's the accuracy of your pointing?
Right now, about 1 degree.
1 degree.
1 degree. Let me tell you, that's been a very, very expensive project. All right.
Any more questions? I think it's obvious. Okay, cool.
So how do you dissipate the heat? This is a question I'd like to understand.
Okay, so, okay.
Yeah.
All right, so dissipating the heat, the usual methodology you would use is some sort of a copper jacket and then just expose it to space and radiate the heat out. What we've done is we've created a 3D printed aluminum jacket that has multiple fissures in it that allows it to expose and radiate much faster. It is an experiment as well. We have a lot of temperature sensors attached to it to see how fast it dissipates heat.
Yeah, very impressive. And also, like, I live in Manchester, so it's very cloudy. Is cloud could be an issue with your technology?
The only thing that destroys a laser faster than the atmosphere is a cloud. Yeah, so it is a clear weather transmission method only.
Congratulations on your SBIR. You said it was an Air Force.
Yes.
Do you see opportunities for, like, American PocketQube builders to do Space Force projects or Air Force in the future?
Yes. As a matter of fact, so I'm going to get into some technical stuff that is probably very U.S.-centric. I apologize. For the United States, we partnered with a team that had experience with SBIRs, and they introduced the whole idea of the picosat to the Air Force. Up until that point, they weren't even looking at it. So what we had to do was convince the Air Force that this is the right path to take. Now, we've pioneered that path. Okay? If you're building PocketQubes in the United States and you go to the Air Force, especially the Air Force Research Lab, they know what we're doing. They'll listen to you. Okay? You have a much better shot of getting an SBIR at this point. 3 years ago, it was not going to happen. But now that is an available avenue. And we do have an SBIR we're working on with the Space Force right now, so that we've broken ground on that as well. As a matter of fact, these SBIRs, they come in phases, phase 1, phase 2, phase 3. We've successfully done a lot of phase 1s, a lot of phase 2s, and now we're looking at a phase 3 and plus an indefinite quantity, indefinite delivery for a constellation. And if we get that, then we've made it. All right? We've made it because then we are making money instead of me constantly paying. SBIRs don't pay that much. Okay?
Very cool project, very cool system. I haven't seen much about what's the data rate that you're looking at, and basically the divergence of the beam. Yeah, kind of the two problems that you have.
Right, and the divergence of the beam, like I said, we're starting with a 30 millimeter aperture on that beam. It's going to be bigger than this room when it arrives. For the absolute technical details, I have to get my laser guy here. Okay, he did not want to come over to Scotland, and I don't blame him. By the way, our laser guy, I'm gonna tout him. Lloyd Spanberger, and you can actually look him up. He developed the forward-looking infrared camera system for the SR-71 Blackbird. He developed the ADCS control system for the Corona satellite project, the spy satellites. and he was one of the first people to build a laser. When the concept of lasers came out in the 50s, his boss at the Air Force wanted one, and so he was tasked with building a laser from scratch. So this is a guy who's got a lot of history. Find the folks with the lots of gray hair and get them on your team. Trust me, it'll save you a lot of money. Okay, does that answer your question? Okay.
So we've got time for one more question for our next speaker. Yes, Tibor. Sorry.
So I know the place that's called the country of blue skies, which have like 308 days of blue skies throughout the year. It's the Gobi Desert in Mongolia. So a good place for a ground station. So the question itself is regarding the uplink. So do you have only the RF beacon, or do you have some kind of RF receiver on board to send up the command?
Yeah, because we wanted to make certain this would work, we do have RF communications. They are in S-band, so we have S-band up and down as well as the laser. So we have the RF beacon, and our communications are all S-band. This is a laser test. If it works, we're going to add the ground capabilities because let's just face it, the surface area of a PocketQube is kind of limited. So if you transmit, where are you receiving? We think we have a way of doing that with our optical telescope that we have, but we have to retune it. So it would eliminate Earth observation capabilities, but it would give us full up and down, which that comes next. Down first. Okay. All right. And
All right. So that sums up the questions.
All right.
So round of applause for Joe.
All right. Thank you, everyone.